Polynomial functions are in this form. F of x equals a n x to the power of n, then a n minus 1 x to the power of n minus 1, all the way down until you have a2 x2, a1 x1, and a0. All of the a terms, so an minus 1, a2, a1, a0, these are just coefficients. They're just numbers. They're written this way so that you have some kind of indexing variable. You know which one goes with which power of x. And you'll notice that the highest power of x is some nth power. All of the n's are just integers. So right here at the very beginning, we have a0 x to the 0. X to the 0 is just 1, so we don't typically write it. That's why I didn't write it there. But it does start with x to the 0. Then you see we have x to the first power, which is just x. You can just leave off the 1 there. And then you have x squared, and then you'd have x cubed, x to the 4th, the 5th, the 6th, all of these things, all up to some n minus 1, then some n. This is just designating the highest power. That's whatever it is. It could be x2, right? If it was x squared, all of these terms just kind of go away, and it'd just be this x squared term, and then x, and then 0. If it's something higher than that, then it could be like x to the 15. This would be like, for instance, 5x to the 15, and then plus 14x to the 14, plus, and then all the way on down, all the terms. So x to 13, x to 12, x to 11, 10, 9, 10, all the way down to, you know, I don't know, negative 1.5x squared plus x plus 1. It could be that. It can be any power of x. So it could go up to 1,000,000. It could go up to 1,000,000,000. It could go up to something. What matters is that it doesn't keep going up. Eventually there is some highest power. And this highest power is very important. It is called the degree of the polynomial. So this is called the degree of the polynomial. So just again, this polynomial has degree n. And of course, some number will be given in an actual problem, but in this general case, we're just talking about the highest power that there are. And the degree n tells you what kind of behavior the function has. Before we talk about the function behavior, let's kind of just get a general idea of what polynomial functions look like. So typically, a polynomial function has some shape like this. So this is just the graph. And we have some shape that goes, it could be a lot of different ways, but it looks something like this. Polynomials will not be things like this. Let's see, let's go like that, and then come down there like that. And you won't see polynomial functions look like this. So the reason why the first one is what a polynomial function looks like is because polynomial functions are what are called smooth continuous functions. That means that they will never have a sharp point like this one does. This is not a smooth. This point right here, let me just circle it out. That is a what's called a cusp. It's a direct point in there. And that has very rich meaning in calculus. But for now, you'll never see these sharp points. It'll always be a smooth curve that you're drawing. Also, it is continuous. And right here for this function, we have a discontinuity here where it jumps. On the left-hand side, it's going up to positive infinity, and then it jumps down to be lower than positive infinity. These are actually called rational functions, and we'll look at them in a later video. But this is called a discontinuity. It's actually an asymptotic discontinuity. This is a discontinuity. And for polynomial functions, they are continuous, meaning you will never have to remove a pen or a pencil from your page when you're drawing it. You can always draw it in one smooth motion with your and always on the paper. That's a very simple definition for continuity. Another type of discontinuity that you'll see is called a jump discontinuity. So that's like if we have a function like this, and it stops, open dot there, and it jumps down and goes like this. This is a smooth function. There's smooth lines and everything, but there's a jump discontinuity there. And to draw this, I had to remove my stylus from the tablet, and then come down here and start again. That's directly tells you that this is not a continuous function. So polynomials will not look like this last one here, only this first one. Okay, so back to our discussion about the polynomials and the degree. So the degree of a polynomial kind of dictates its behavior. You can always look at the degree and tell what is the end behavior of a polynomial. The end behavior is just kind of where it goes as x gets very large or very small, or very negative, very positive or very, very negative. So on the graph, right, this is very positive x, and on the left-hand side is very negative x. As you keep going left, you get towards negative infinity. Keep going right, you get towards positive infinity. So the degree of a polynomial, so if I look at very simple ones, x squared, the degree of the polynomial, this is the x squared function. I could write whatever I want on here. It's not gonna look the same thing, but like I could write 3x plus 1. The degree, in this case, the degree is 2, that's the highest power of x, dictates the behavior of the end behavior. Meaning that as x gets very negative, we go up to positive infinity. As x gets very positive, we go up to positive infinity. It goes up and up on both sides of the function. Now, this is like opposed to if we were to look at something like x cubed. X cubed looks something like this. And you see, as we go towards negative infinity, we go down. As we go to positive infinity, we go up. So the x squared function had similar end behavior. It went up and up on both sides. The x cubed function had opposite behavior. It went down and up. Now, this is always a theme between even and odd powers. You'll notice that the x squared, right, this is an even power, and the x cubed has an odd power. So even functions will always have this type of behavior where it's the same in end behavior, goes up and up. Whereas odd powers of polynomials, odd degrees I should say, have opposite end behavior. These can be changed if there is a negative coefficient in front of it. So like if the leading term is negative, so I'll put it in blue here, the leading term is negative, then this will be the polynomial we're looking at. And here we see we go down and down from both sides, down and down. You notice though that they're still the same direction going down. That's because it is a squared or an even degree polynomial. And a cubic, if we had negative x cubed, it would look like this. And you see we go up and down. Just the exact flipped, but they're still the same. The different sides go different directions. That's the big thing about odd degree polynomials. So here I have a few functions that are, I'm going to graph here on Desmos, and we'll look at the end behavior. The first one is 3x squared. This one you can see it goes up and up on both the left and the right hand side. That's because the degree is even powered and it is a positive leading coefficient, as it's called. The 3 here is the leading coefficient, and that will determine if the polynomial gets flipped or not, so that like even functions, instead of going up and up, they go down and down, and then odd going down and up, flipping that, going up and down. Because it's positive, it's going to be the normal behavior, namely up and up. As you go to the left, you can see that it just goes up and up and up and up. And then as you go to the right, it goes up and up and up and up. Just keeps going up. The next one, the degree is x to the 6th. And you'll notice that the leading coefficient is negative, meaning instead of going up and up on both sides, because it's an even degree polynomial, it's going to go down and down. If I graph it, there you go. You see that it goes down and down. And I'll just keep going down as I keep zooming out more. Okay, for this next polynomial, we have a leading coefficient of 15. So it's an odd power, so we expect it going to the left, it should go down. Let me just show you that real quick. X to the power of 3. We expect this behavior for the 15x to the 15 minus, what is that, 10,000 x to the 14. It goes down as we move to the left, and it goes up as we move to the right. That's the behavior we expect. But when we graph it, it looks like it goes down on both sides. That's because this coefficient in front of the 14 is much larger than the coefficient in front of the x to the 15 power. It dominates when x is small. However, the leading coefficient, or sorry, the leading term, the degree of the polynomial, the biggest power, will always dominate no matter what. I could add as many zeros as I want on this thing here. I could add as many zeros as I want. Eventually, the first term here, the 15x to the 15, that will dominate it. At some point it will. And all we have to do is find that point. I should take off a couple zeros. It's just going to take forever. You'll eventually find it, but if I take off a few zeros, you'll see it faster. We go to 10,000 or 1,000. See if I can find it faster this way. And there you go. Okay, here I've labeled from negative 50 to 150 on the x-axis. On the y, I'm just going to start adding zeros. And what you're going to see is that we eventually see the point at which the function stops going down and down on the left and right side, to where it eventually will go up on the right hand side. So the degree of the polynomial, the leading coefficient, and the degree, the highest power of x, will always dominate. You just have to go far enough out and you'll see that. In this case, we had to go out to 50 plus, and then we can see that it doesn't indeed shoot upward as we keep going out. No matter how big this zero is, right? If I add a 0, it looks like it goes back down again. But all I need to do is zoom out a little bit further, and there it is. It showed up again. Add another 0 to this. Once again, it looks like it's going down and down. You just zoom out far enough, and there it is going up again on the right hand side. So the degree will always dominate it, and you should always expect the leading coefficient and the degree to dictate the end behavior of a polynomial. All right, for this last one, we have a negative leading coefficient with a degree that's odd. So we should expect it going up on the left-hand side and down on the right-hand side. And that is, in fact, what it's doing. So that's how you can use the degree and the leading coefficient to determine the end behavior. It's only when x gets very large, positive or negative, that's what the end behavior tells you. Another very important topic about polynomial functions are the zeros or the roots or the solutions. They all kind of mean the same thing. And the zeros, roots, solutions, whatever way they're saying it in the problem. I prefer zeros because it's directly mean to what we're saying. The zeros is just when is the function equal to 0. We can very easily set a function equal to 0. We just move everything over to one side if it's a mess on both sides. But the way we solve this is, you should actually already know how to do this, factoring. We're going to factor this thing. Now this is actually a cubic polynomial, so we can factor this thing by doing factoring by grouping. So we just ask, what can I take out the first two terms? Take out an x squared. That gives me x plus 7. And out of the next two terms, I can take out a negative 4. That gives me x plus 7. And then I can factor out the x squared minus 4. Sorry, the x plus 7 from both terms. That gives me x squared minus 4. And then x plus 7. And x squared minus 4, this is a difference of two squares. The first thing is x. The second thing is 2. So we have x plus 2 and x minus 2. And then x plus 7. Of course, these are all equal to 0. And my zeros, my roots, or my solutions to this thing are going to be x equal to negative 2 from the first factor there. This one gives you negative 2. This one gives positive 2. And this one gives negative 7. So those are my zeros of this polynomial. Now, what are the zeros? So you should actually already know what the zeros are of a polynomial. When the function equals 0, that's the same thing as asking when does y equal 0. And when y equals 0, you get your x-intercepts. And you'll see here that we have x equal to negative 7, x equal to negative 2, and x equal to positive 2, which are the three zeros we found when we factored it. So why do we want to find this? Again, it's very easy to set a function equal to 0 and then to solve it using factoring or many different strategies that we have. That's the reason why we study factoring and everything like that, because that's how you can find these important points of polynomial functions. Now for this one's pretty much already factored, so the zeros are really easy to find. And here we have x equal to positive 2, that's from this first one here, negative 3, that's from this one, and positive 4 from this last term. Now in the previous problem, you may notice that we have 3 zeros and we have a degree of 3. In this one, we have 3 zeros. However, if you were to expand this thing out, this whole polynomial function out, you'll end up getting 7x to the 6th and then plus whatever else is there. This is the degree of the polynomial, it's 6, and the leading coefficient is 7, but that's not really what we care about right now. But if I notice that this 2, right, this thing gave us 2, and it has a power of 2, then what I could think of this as is saying like there's actually x equal to 2 twice here, because if I were to expand this, it would look like 7 x minus 2, x minus 2, x plus 3, x plus 3, x plus 3, and finally x minus 4. And you'll notice that there is x plus or x minus 2 twice. So there's actually then we have negative 3 3 times and 4. However, there's no reason to write it like this because x equal to 2 and then x equal to 2, it's the same 0. It hasn't changed anything. But we can designate what this is called by saying 2 is of multiplicity 2. 2 is twice. Negative 3 is of multiplicity 3. There's 3 negative 3's as a 0 for this thing. And of course 4 is just of multiplicity 1, which is just 4. There's no reason to say multiplicity. The reason why this is important is because if we count this, we have 2 here, then we have additional 3, so that's 5 total, and then we have 1 from this one, so we have 6 in total. And that matches the degree of the polynomial. I'm going to talk about this more in the next video. It's called the linear factorization theorem. It's very important for polynomials, and polynomials are very important functions. But just kind of keep this in your mind for now, and we'll move on. So zeros of polynomials are very important numbers. They're kind of like prime factors for numbers in general. Every number can be factored down into a unique representation of prime numbers that are multiplying each other. Well, the zeros of polynomials are like the prime factors. They're not necessarily unique, but they are very important for us to find because they solve those problems where the function equals 0. And that's easy to set up and makes it easy to solve for. So finding these zeros are the most important thing. Just what are techniques to finding these things? And one of them that we can use is the intermediate value theorem. This is actually a pretty obvious theorem, but in mathematics we don't take anything for granted. We have to have a theorem stating something that may seem obvious. You have to have a theorem to state it to actually use it. And this is the theorem that says it. It's very simple to use. If I have a function like this, and I have, I don't know, some polynomial, whatever it is. If I say at some point here, this is above the x-axis, therefore f of x is greater than 0. And if I have some point down here that says f of x is less than 0 because it's below the x-axis, then the intermediate value theorem says that between these 2 points, at some point, the function will hit 0. And it does, in fact, hit 0. It hits it right there. And this is based on the fact that polynomial functions are continuous. In order to connect this top point to the bottom point, you have to draw a line that can't jump. You have to draw a line somehow. So, for instance, if I were to draw a function like here, and I were to tell you that the function is negative down here, and the function is positive up here, and I were to draw a polynomial here like this, I could draw it, and I could spend as much time as I want down here. I could do whatever I want, but at some point I have to cross the x-axis to hit there. Of course, the way I graphed it doesn't double back on like I did here. This wouldn't be a function. It would always move forward. Maybe that's more realistic. I'll just ignore that part. But at some point, I have to go up and I have to touch that point because the polynomial is continuous. So right here is the 0 of this polynomial function. This is the polynomial that I had before, and I factored into these 3 things. So we know that there are zeros at 2, -2, and -7. And just to kind of show how the intermediate value theorem works for something that we know, so that we know where the zeros are, if we were to test some things like x equal to -8 and -1, these are around this x equals to -7, 0. And so we should expect one of them to be positive and one of them to be negative, whichever way it is. And if we were to test that, right, we'd have f of -8 gives us -8 to the power of 3. It's going to be -512, then plus 7 times x squared. It's going to be 7 times 64, giving us 448. Then -4 times -8 is going to be 32. And finally, -28. So this gives us -512 plus 448 plus 32 minus 28, and that gives us -60. Okay, now f of -1. -1 cubed is -1. -1 squared times 7 is going to be +7. -1 times -4 is +4, and then -28. If we test this out, we get -1 plus 7 plus 4 minus 28, -18. Okay, so this one I completely forgot that between -8 and -1, we have 2 zeros between there. So there's no guarantee that you're going to find a 0, even though there are zeros between them. What you have to do is you have to take small increments between the numbers. You can't take large increments like this. You have to take small ones. And once you start to find a difference in the signs, that's when you're good to go. And this you can see definitely is true when we plug in x equal to -6. X equal to -6, we just take -6 into the function. And let me do that real quick. Doing this gives us 32, which is positive. And because I have right out like this here, f equal to -8 is less than 0, and then f equal to -6 is greater than 0, and then f equal to -1 is less than 0. I know by the intermediate value theorem there must be a 0 between these two, and there must be a 0 between these two. And of course there is. X equal to -7 is a 0. X equal to -2 is also a 0. So that's simply how intermediate value theorem works. It's pretty obvious when you really think about it and you know what continuous functions are, but it does give us a strategy to find zeros by plugging in test values and seeing if they're positive, if they change positive to negative. Okay, one final property for polynomials is that polynomials can have up to n-1 turning points. So for this first function, we have x to the power of 5, the degree is 5. That means at most it can have 4 turning points. 5 minus 1 is 4. Turning points are just where it shifts from going upward to downward. In this case, we have a function that's going up and up and up, and then it kind of levels off, and then it goes up again. There's not really any turning points there. Now, if I have a more interesting polynomial that has more terms in it, then you'll see here that there is a lot of turning points. We start off going up, and then we shift right here at -1.57, and then we go down, and then at -0.592 we go back up. Then at 0.183 we go down, and then we go up again at 1.179. So there are 1, 2, 3, 4 inflection points. There can't be any more than that. Once you have 4, because 5 minus 1 is 4, that's the most inflection points you can have. And that's because the end behavior has to go down as we go to the left and up as we go to the right. If there was another inflection point, it would in fact go down and down on both sides. So you have to have n-1 inflection points at most. So that's this one. Let's look at x to the 8. At most, there can be 7 inflection points here. There's really only 1 in this case, right? It's going down as you go to the left, and then it goes up as you go to the right. But if we have a more interesting one, right, this is still x to the 8 as a degree, so it can have as most 7 inflection points. This one has, as we're going down as we go left to right, going down at this point here, we go up, then we go down at this point, and then we go up at this point. So we have 3 inflection points. And the end line behavior, or the end behavior of this polynomial, is still up and up on both sides because it's an even degree polynomial and it has a positive leading coefficient.